A generic definition of machine learning is the field of study that gives computers the ability to learn without explicitly programmed. If you have touched the industry of machine learning, if you have did some practical stuff, if you have watched some videos about machine learning, you would probably read this statement before, right? The technical definition of what is machine learning. When a computer is said to learn from experience with respect to some task and some performance measure, if its performance on the task is measured by the performance, it should improve with the experience. Okay, what does this mean? Let me give you an example. Say that we want to do a classification of spam email. It means we have tons of email and we want the machine to automatically classify for us which are the spam and which emails are not the spam. So remember that we need three things. We need experience, we need task, and we need performance measures. So what is the E here? The E experience is the examples of email, right? The spam and not spam email are the examples. We need examples of spam email to show our computers. We need the examples of non-spam email to show our computers. What does it look like to have a spam email? And what does it look like to have a non-spam email? And the task, what is the task we're trying to do here? The task we're trying to do here is to flag whether these particular email examples is a spam or is not a spam. Experience is our training data, right? The data that we have, the examples of spam email and examples of non-spam email. And the performance can be measured by various evaluation metrics, right? Now that I'm showing here, I show only accuracy because in general, how do we measure our success, whether this model is a good spam email classifier or not, right? Ultimately, we look at accuracy, whether this, how many percentage of the supposedly spam are classified as spam, how many non-spam emails are successfully classified as non-spam, right, for accuracy. But in the machine learning industry, if you are a data scientist or machine learning engineer, you know that this accuracy alone would not be suffice to all of the situations, right? Towards the end of the day, today we will talk about a little bit about that as well. Okay, so the accuracy to measure our performance generically is the ratio of correctly classified emails. All right, so this is how we measure our performance. So machine learning requires three things: a task, experience to train the models to fulfill the task, and a performance measure to measure how well our model can fulfill the task. This is what a comprehensive definition of machine learning is supposed to be. Okay, so why should we use machine learning? There's a couple of reasons why, and the machine learning industry has been very, very matured, especially in the images and video, and also e-commerce. These kind of industries are very, very matured in using machine learning technology, right? And unfortunately, in the business industry, is not that mature yet. Okay, so the traditional approach of what we do to classify a spam email and non-spam email, we would look at what a spam email typically looks like. We look at the emails in our inboxes, all the emails we received. We look at the words that are suspicious or that are usually appear in our spam email, right? Like for you, credit card free and amazing deals, things like that. So we'll look through the email, we'll read one by one, and we would check which terms, which words are usually appear in our spam email. We would also try to identify the patterns in the sender's name, if their domain name is something fishy, their email body, uh, they might have some images that are not supposed to appear in business emails and things like that. Then we will write rules to flag emails as spam. If you see if you see credit card, then it is a spam. If you see free, if you see amazing deals, then it's a spam. Right? This is a traditional approach to classifying spam email. But as things will constantly evolve, right? So are the spammers as well as scammers, right? People change. The same trick won't work all the time. So when the spammers evolve, right, you have to redo your traditional approach again. You have to search for the new words that they use. You have to search for new patterns that what a spam email typically looks like and things like that. So it would require a lot of human resources, a lot of time and energy to look into the emails, to identify the patterns, and to update your rules that you return to classify the spam email. What is the problem here? The problem here is you would have a very long list of complex rules because there's going to be a lot of situation where this email is a spam, right? You'll need to see this word and this word, then you classify as a spam. In another scenario, you might have the combination of this word and this word. So you have to write out all the rules together to classify as a spam email. And it's very difficult to maintain because, as I said, people evolve, right? Spammer evolve, scammer will also evolve. So as your spam classifier improves, if you have add more rules to your spam classifiers, your spammers will also change their strategy, change their techniques, change the word they use, and you have to keep up with the speed that they change. And typically for human is not possible to do that, right? So what machine learning approach will help in that case would be the machine itself will learn from the data, right? It will learn from the example emails. It will continue to learn as time goes, as more and more new data comes in. The machine will learn automatically 24 hours, no break time, no weekends, no TGIF and everything. So it will continue. You learn from new examples continuously, or if you don't need it to be continuously, you can schedule regularly, right? Like once a month, once a year, and things like that. And then since the machine is learning from data, you wouldn't have a bias from humans, right? Humans have their own feelings. Humans are limited to our knowledge and our patterns, our biases. But machine does not have feelings. They don't have biases in their mind, right? Unless you as a machine learning engineer, uh, when you're training your models, you have added some bias into your models, right? That could be, but assuming that the machine learning engineer does the right thing and trying to avoid biasness technically, the machine should not have too much of a bias because it can learn from the data. The data will tell the model what is right and what is wrong. The machine itself wouldn't have its own subjective opinion or its own feeling of what is supposed to be right and what is supposed to be wrong. So what's best is this would be an automated process, right? Imagine you can, you know, you no need to accommodate resources, you no need to hire a team of 10, 20 staff to read emails and find words of what is a spam and what is not a spam, right? I mean, that's a waste of resources, right? People, imagine your job is sitting there 8 hours, 9 to 6, overtime maybe, and your job is just to read through emails and find words and write rules to classify spam or not, right? Imagine how boring is that task if you are the one who do it. So it's not efficient, and it's going to have a lot of human errors and a lot of things, right? So this is machine learning. It doesn't apply to only uh, spam emails. Is just an example that I use. It could be house price prediction, demand forecasting, and forecasting the demand of next month. Machine breakdown. I'm not going to have someone stand by the machine 24 hours. Well, that's basically what a lot of manufacturing companies do today. But imagine if you can save that resources by having a machine to check through your sensors data to predict whether your machine is going to break down or not and send you an alert before it does, right? So imagine you have a machine to do that for you. You might be able to accommodate your resources more efficiently. You might not need a staff to stand by 24/7 just in case the machine breakdowns, right? So this this kind of advantages applies to a lot of industry, right? And the most the industry that benefits the most from this is the thing that all of us are familiar with, which is social media, e-commerce, right? The moment you finish your YouTube videos, the uh, right next second, the video YouTube already recommends you a list of videos you might be interested to watch, right? E-commerce, when you buy a product, in few seconds, Amazon or Shopee already recommends you the next 4, 5, 6 item you have to buy, right? And because of that, you're getting poorer and poorer, right? And all these things are automated, personalized, customized to your needs, right? And sometimes I just feel like the social media knows me more than my family or my parents do, right? They because they already know what you want to buy, even when you yourself don't know that you need it, right? And when the recommendation comes out, you just can't help yourself, but you just press the add to cart button or buy now, right? So yeah, imagine the e-commerce platform, the social media platform knows what you like better than you know yourself. That is machine learning, right? That is personalized experience. And more and more, I mean, the trend is going towards this direction, right? Highly personalized. We cannot possibly do this a few years ago or a decade ago, because the industry is mass production, right? That in that era, the trend is mass production, standardization, right? T-shirts, you only have S, M, L, XL, a few sizes. But imagine from machine learning, I can personalize, I can tailor your the products, your clothes just for you, right? And what's better is I don't need a human to be there uh, to serve you for these personalized or customized products, because we can learn from data and the machine will decide what is the best for you. Okay, so that's the high level view, basic concept of machine learning. So let's go a little bit technical, right? And take our first step into machine learning algorithm. So machine learning algorithm, when we talk about the type of machine learning, we usually look at whether that machine learning algorithm requires human supervision or not. So if the machine learning algorithm requires human supervision, it is called supervised learning. When it doesn't require any uh, human supervision, it's called unsupervised learning. So you might be wondering, because I just said that machine learning is fully automated, it doesn't require any human input, and now I'm talking about needs human supervision and not human supervision. Aren't you supposed to be all of them are not requiring human supervision? The answer is yes and no. So when I say I need human supervision, it doesn't mean I need someone to sit there, look at the machine, and tell them what to do. That is not what I meant when I say human supervision. When I say human supervision, I mean the data, right? So here is my data. Here is the labeled data. And then here are the labels. Okay, the human supervision here is we need to tell the label, what is this about? What is this data supposed to be? So I will show you an example later. But here you have your data, and then you need someone to label the data. Okay, you label the data and then put into a model, machine learning algorithm, and the model will learn from the labeled data, will learn from the data and the labels that the human labeled. Okay, so I labeled the data, push the data into the models, and the model will learn from the data, and it will make prediction based on the new set of data and output a result. Okay, what I mean by human supervision, what I mean by labels. Remember that we said just now, spam emails or not spam email, right? The machine will learn from the data automatically what is spam and what is not spam. But where is the human input? The human input will be labeling the email spam is a spam or not. That requires human input. Okay, but it's not necessarily human input, right? Even this human input can be automated. What do I mean by that? For example, in manufacturing industry, right, we have a lot of machines, and then when we want to predict machine breakdowns, right, the labeled data is the sensors reading of the machine, and the labels here is the input to the data to label whether this machine break down or not. Okay, then we have a column, machine breakdown, yes, no, yes, no, yes, no. Okay, and that label actually doesn't require human input, because if you're a manufacturing company, if you have a few machines in your company, then chances are you are going to have an automated system that records for you when the data breakdowns, isn't it? Right? So when your system breakdowns, automatically the system can capture that information and writes the data into your raw data, saying that at this time the machine breakdown. This labeling can be done by a machine, right? So it's in this case, it doesn't require any human input anymore. You get the idea? So yeah, when I say human supervision, that is usually the case for some very difficult tasks that cannot be automated. Like for example, image recognition, or face recognition, or object recognition. So uh, like a camera that automatically detects your face or a human in the videos, that requires someone to manually look into a video and draw a square box around a human or the object they're trying to identify, right? That requires human input. So, and then for machine breakdowns, like I said just now, that doesn't require any human input because the system can already capture itself for you. Okay, so yeah, that's why the answer is yes and no. Sometimes you might need human input, sometimes you might not need human input. If you can automate the human input part, then you doesn't require any humans to do any work in the machine learning process. So here, an example of supervised learning is classification, right? The examples that we used just now is spam email classification. The training set here is our labeled emails. Okay, so this labeling here is going to require human input because the machine might not know what is a spam look like, right? So this is something you need to do. But the difference between machine learning approach and the traditional approach that do all the manual work is that the only human input requires here is the labeling process. All right, it's just the labeling process that requires human input. The training process, the rules of whether it's a spam or not, is fully automated and trained by the model itself to predict the new unknown data, which is a new email. All right. So terminology alerts here. Sometimes you might see I use the term instances, examples, right? These are actually your data. Okay, your data, or you can think of it as rows in your maybe Excel file or CSV file, right? You have columns and rows. So one row is one instance. One row is one example. Okay, so please don't be confused when I use the term instance or examples interchangeably because they mean the same thing. Okay, and then another example of supervised learning, I'll call it regression, right? It's called regression. The difference between classification and regression is for classification, you have something to classify, spam or not spam, right? Machine breakdown or not. But for regression, you do not have yes and no. You do not have ABCD, but instead you are predicting a value. What is the value of the price if I have 2 bathroom, 5 bedrooms, 2,000 square feet and 2 floors. What is the price of the house? Then this problem is not yes and no anymore. It's not spam or not spam anymore. It's 0 to infinity, right? The value of the price of the house can be anywhere along the numerical line, right? The real number line. So this kind of situation is called regression, right? Not just the prices, we can maybe forecast the demand of something, or the temperature of our sensor reading, temperature of our machines, the age of someone. All these are regression problems, right? And they requires some human supervision, which is labeling, because if I want to predict the temperature of a motor, and then I have the sensors data as a predictor, then I would need a long list of different sensor readings and the temperature of the motor to train a model. So this can be automated because even the temperature of the motor can be captured using sensors, right? So even though the label is uh, motor temperature, you can automate that process using a heat sensor or something. So, and then let's say I have modeled my machine learning algorithm. When I have a new instance coming in, okay, along this feature, I will just find the value from my model. Okay, so this is supervised learning. What about unsupervised learning? For unsupervised learning, it doesn't require any human input because you are not going to have a label. Okay, so here for my raw data, okay, for my raw data, that is, it could be unstructured, it could be structured, it could be anything, right? Whether it has a label or not, it doesn't matter because here the label doesn't serve as a label anymore, right? So, and then the machine, okay, will look into this data, it will grind the data, and then it will interpret the data, push into the algorithm, and then it will split the data into different groups. Okay, so this is called unsupervised learning. An example of unsupervised learning is customer segmentation, right? Or the use case here could be targeted marketing. Let's say you want to sell some clothes for female, right? Then you have a long list of leads. You have a long call list. You want to, call someone to buy your clothes, which is for female, right? So maybe you are a luxury shop. You are targeting rich people. So, but rich people might not want to buy your clothes. So you want to look into your historical data. Who are the ones who usually buy from us, right? So in this situation, we would push all the customers' information that we have, the data we have about customers, their income, their age, their occupation, and things like that. Then we'll pass into our unsupervised learning algorithm so that the machine learning algorithm will grind the data and output a result to you to group them into different groups, right? Then from there you can label who has bought from you, who has not. So from there you can see these clusters of people has higher chance of buying from us. All right, so in the call list, I would prioritize this group of people first because they have higher chance to buy from us. Okay, because of their similarity. So clustering or unsupervised learning, I mean, this approach is called clustering. We divide our data into different clusters, but we do not know who they are, right? Here, the executives, the soccer moms, retirees, students are labeled by me, the interpreter, right? The machine will not show you this interpretation. You are the one who needs to put a label on them, okay? Or to investigate on these clusters, on this data, that who they are, what's the characteristics, and things like that. So another thing is dimensionality reduction. This has nothing to do with any business case, any uh, business operations, because this is a pre-processing phase for your machine learning training. Okay, before you train your model, sometimes, for example, if you have a huge machine that has 1,000 over sensors or a few thousand sensors, right? One sensors will take one column. So when you want to predict whether your machine breakdowns or not, you would grind into that 1,000 over columns. Imagine you have 1 million rows. Then how many data do you need to grind to? 1 million times 1,000, right? Is 10 billion of data. So in that case, that will consume a lot of resources, very, very highly cost, because computing power is not cheap. Okay. I'm not talking about 16 gig RAMs, I'm not talking about 32 gig RAMs, because when your data gets larger and larger and your model gets even more uh, complicated and complex, you are not talking about gigabytes of RAM, right? That requires some numbers that we have never heard before. Okay, that's why cloud computing is getting so much attention today, because of machine learning algorithms. Big social media companies, e-commerce companies like Amazon, they are doing cloud computing. Why? Because the algorithm that they use and the data that they are working on is huge, it's tremendous. So that is not something a laptop can do anymore. It requires a cloud computing server so that you can scale up the computing power easily. Okay. So that's why we need dimensionality reduction. So we grind through the columns and the features, and then we will look at which columns are useful, which columns are not, and we'll try to squeeze the 1,000 over columns into, let's say, 10 or a few tens of columns, right? That would be much better than 1,000 columns. So that is the function of dimensionality reduction. Okay, we're trying to reduce the complexity of our data so that it's easier to train our model without losing too much information. So for when you're dealing with large data sets, it's often a good idea to reduce your dimension of your data, to reduce some columns, number of columns, because you run much faster. You take less cost, it will cost you less, and in some cases, in fact, in a lot of cases, it would perform much better. Okay, so in machine learning modeling, is not always the more the merrier. Sometimes the more data you have, you incur a lot of noises into your data, a lot of useless information into your models, and your model will thought that is some good information, because it cannot differentiate good or bad information. Okay, so in machine learning, it's always the data that input is very, very important. When you feed garbage to the machine learning algorithm, right, the machine algorithm will output garbage for you because it learned from that. Whatever you feed the model, it will learn from that. So be very careful on the data quality that you feed your machine learning algorithm. Another use case of unsupervised learning is anomaly detection, right? Prevent fraud, catch manufacturing defects. We look at the sensor readings of a machine, and then we would try to cluster the sensor readings in different groups, and the cluster that stand out, right, is the cluster that have abnormal behaviors, right? What do I mean? When you see the data are sitting close together, so when they are close together and you have someone who stand out, right, it means it's abnormal. So in clustering, it would usually group the nearer one together, and then the abnormal one will be another group. Okay, so in this case, we can identify the clusters that have very little numbers of instances. That would tell us that those instances are abnormal. Okay, so yeah, this is to identify what is abnormal, what instances are abnormal. So if you have a fraud, right, fraud happens every day, but it is very little compared to normal data. So whether we want to take out the abnormal data or not, it depends on what you're trying to do. If let's say I want to predict my house prices, right, then I will find the abnormal one. For example, a wooden house in Kampong, right, that costs you 1 million ringgit Malaysia. Is that information useful to predict house price? No, right? Because that is an outlier. I mean, who would buy a wooden house in Kampong area with 1 million ringgit, right? So that information is not useful in predicting your house price. We will remove it. But if I'm trying to identify fraud, who are the scammers, who are the frauds that are trying to scam my company's money, the position here will be entirely opposite, because now the abnormal data is what I want to focus on. I don't care about my normal customers because they are just doing their own transactions. Why not? Why do I spend time on that? So the time I want to spend here, my energy I want to spend here is to identify the abnormal people who are trying to scam my money, which is very little percentage of my customers, right? Let's say 0.0001%. So that in that case, I shouldn't remove the abnormal data, but I should focus on that data. I will pass to my compliance team, maybe I don't know what team you call, but they would investigate on this person, call them, hey, why do you do this transaction? Then get their justification and all that. So that abnormal data is what I want to spend time on, right? Manufacturing defects, if I have abnormal sensor readings, should I just ignore the abnormal sensor readings? No, I should check that sensors, what is wrong with my machine. Maybe the temperature is too high. I want to look at the temperature. Is my coolant enough? Is the ventilation good enough? Is the cooling system working? So, right? So it depends on the situation and your task. Okay. For the next one would be association rules. Association rules is exactly what I talked about just now, right? Recommendation system, social media, Shopee, Lazada, they know what you need better than you, right? Because they are using association rules to discover relationships between your items. Okay, if you buy an iPhone online, then most probably you would need to buy an AirPod, right? If you buy, let's say, a book from Amazon, it will recommend the next episode to you because that's what most people will buy next, right? If you buy, I don't know, moisturizer, then you might need to buy a toner or face mask or things like that. Okay, so it will look into your purchasing behavior and the purchasing behavior of other people that are similar to you to predict what you're going to buy next. Okay, so yeah, that is machine learning. So the typical process, now we are getting more technical, okay, because you're going to look at the whole process of machine learning. Okay, that's the objective you're trying to achieve today. From raw data that I gave you just now, we want to start from scratch, read the raw data, and eventually train a model to predict something. Okay, that's what we are trying to achieve today. So a typical workflow of a machine learning process is this. Question or problem definition, right? First, like I said just now, machine learning algorithms requires a task, experience, and performance measures, right? Performance measure is something you want to examine, like accuracy, and then for experience is the data, right? But the first thing you need to identify is the task, what you are going to do, what you want to do. That is the most important part. A lot of times when we deal with clients and when we ask them what are you trying to do, they will tell us that I don't know. But I have a lot of data and I want to use that data for prediction, to do predictive analytics, because that's the hype now, right? That's a trend now. So we cannot miss this trend. The fear of missing this opportunity. So we want to get into this as soon as possible without knowing in the first place what do we even want to do. But this is a very big mistake because doing it for the sake of doing it, there is no task, there is no objective in doing that, right? And this is how most data science projects fail. You're doing it for the sake of doing it without a solid reason, without solid goal. You won't have the right direction to do. And during your modeling process, you have a lot of decisions. When you have a lot of decisions to make, you don't know what decision you should make because you do not even have a goal in the first place. Okay. Acquire training and testing data. We'll talk about training and testing sets later, but this is after you identify the problem, the business objective. The next important thing is to get your data, get your hands on your data, to understand your data, right? And then only you will start preparing your data. You check, you wrangling on the data, prepare data, clean the data and everything for modeling. And then we would analyze, okay? We check the data distribution, correlation between features and the labels, and usually we do this by visualizing the data. And then feature engineering. So the process of wrangling your data and analyzing your data is an iterative process. Okay, when I start cleaning my data, okay, the first time I clean the data, I analyze with my charts and graphs and so on. Then I might have identified other patterns that I wouldn't see before this, right? Then I will go back to the wrangling process, do some more wrangling, do some more preparation, come back and analyze again, right? And most of the time, this is where machine learning engineers or the data scientists spend their time on. Okay, 90% of the time is spent on the first four steps, and the fun part of modeling is actually just 5 to 6% in your entire data science project. Okay, yeah, so that's a little bit of myth busting there. And yeah, the fun part, training and evaluating the model and deploying the model to production is actually the last part. And it usually takes around 5-6% of your entire data science project. Okay, so if you want to be a data scientist, be prepared to do the dirty work, clean the data most of the time, and be frustrated. Yeah, you always be frustrated when your work is always wrangling the data, and you might realize you won't even touch any modeling in the, I don't know, for maybe years and of your working life. Yeah. Okay, so that's the truth. So this is how the workflow should look like when you're working with clients. This process is a typical process when you are a developer or you are playing on a toy project, like what we are going to do next, right? But when you are working with clients, someone pay you to do something, that usually would take another process, right? And we call it Christian. So what is Christian? It usually looks like this. We start with business understanding, right? Quite aligned with our what we said earlier, and then data understanding. And the thing here is your data, your business problems is not yours anymore. It's someone else's problem. It's someone else's data, right? Like for me, I'm a data scientist. I do not have my own data in my company. I don't analyze my own company's data. I do, but that's not what we do for our business, right? Our business is to help clients to analyze their data. So most of the time, we will spend a lot of time in understanding the nature of their business, the problem that they have, the objective they want to achieve, and then that would differ a lot from telco to banking to manufacturing to this and that. And the more projects you do, you are going to be an expert in everything already, because you need to understand everyone's businesses entirely in order to analyze their data for them. And data speaks louder than anything, right? So if you understand someone's data, it means you understand their business even better than their boss. Okay, because data is the truth of everything. Okay, and you understand the business, you understand their data, and then that usually takes a lot of time already, because imagine you're jumping into entirely new industry, right? Suddenly you're an engineer, suddenly you're a surgeon, suddenly you are, I don't know, telco, banking, finance, insurance, and etc. Right? So that would take a lot of time, and what takes even more time would be your data preparation. Okay, because for most company in Malaysia, unless for the big boys, right? Not probably not just in Malaysia. If you are not in a very highly developed country like the US, China, probably their data is very bad. Okay, unless you are in a multinational company corporation, you're in a big corporation, you're in big company, they have their dedicated data engineering team to clean the data, put everything structured, build the pipelines and everything. Otherwise, the data is going to be very bad most of the time. Okay, so this would takes us a lot of time in replacing the missing values, finding the errors, the outliers, the data types, and things like that. Right? Date are not defined as date; it's defined as string. Right? So if you know programming, if you know IT, right, the difference between string and date is what makes you headache all the time, right? Dealing with dates, dealing with time, that kind of thing, data types is very crucial in modeling, in machine learning, because every machine learning algorithms are unique, right? And they have different circumstances. Some can take numerical data, some can only take nominal data, some can only take numerical, some can take both. So what do you need to do so that you can prepare your data for all these different situations? Okay, and after all that part is the fun part, all right? Modeling, which takes around 1 to 2 days out of your whole year of project's duration. Maybe your project is 1 year, but you take only 1 week to do the modeling. Okay, that's the truth of modeling. And then evaluation is an iterative process. I built this model, I check the performance. It's not good, I build again, check the performance again. Not good enough, do it again, compare different models and things like that. And when I finally satisfied with the model, then I would deploy to production. It means use this model to predict the new data. This is what I mean by deployment. Okay, but if it's not good enough, then usually we would run through the whole cycle again, back from starting from your business understanding and all the way up again. Okay, so this is going to be an iterative process. Okay, so let's go to our hands-on. Oops. You might probably want to open the link already. Give me a second. So yeah, I'm opening my drive now. So you might want to take this time to open that as well. Can you share the link again? Yeah. We will share the link in the comment again. And then also check the description box. There will be the link there. Okay. Let me go through the comment first if I miss any questions. Also, take this time to ask questions if you have something you don't understand. depends on your test. Might be good for, might, anyways, might be for a good reason. Sake of spotting an error, take off. I hope. Yeah, thanks Prince for answer. Yeah, that's the drive link and also the collab links. Okay, the collab link as well. Okay, thanks. Do let me know if you cannot access or anything, then we will try to solve it, but for now looks like it's okay. So I'll just go on with what you are going to do. Here you go. So when you are here, please download both of these data. Okay, please download this data. Let me know if you can download or not. You should be able to download, and then when you have downloaded, come to your core lab, right? Come to your core lab and create a new folder. You want to create a new folder here, name it as data. Okay, name it as data, and then right click on the data folder, upload the Titanic train and Titanic test into the data folder. Okay, a very important thing, data folder must be data, because in the code that I give you, I have put the name data in a directory. Okay, so you need to put it here and try to run this thing. Try to run the first two cells, this cell and this cell, to see if it gives you an error. Okay, make sure you do not have any error when you run these two cells. Okay, then you are good to go. And I would appreciate if you can type done in the chat, in a comment, to let me know that you can do it. Okay. And while waiting for you to do that, if you have question, can still ask in the comment when I go through the explanation of the data and everything before we start. So here is the question and problem definition. So this Titanic, okay, is actually a toy data set, which means it's not the real Titanic, right? It's not the real Titanic, but the researcher tried their best to simulate the data distribution so that, you know, it's when, even though it's a toy data set, but it can be useful to learn. And in fact, if you have learned a little bit of machine learning before, probably you have played with this data set before, right? This is like the, you know, the chapter 1 of machine learning for most people. Okay, so yeah, so for those who survive and did not survive the Titanic disaster, then we will build a model to try to predict whether these people are going to survive a Titanic or a shipwreck or not. Okay, so we do have train and test, right? Train and test. If you run this, this one is to read you all the libraries. This one is to help you to get the data, to read the data. And then when you run the fourth cell, you can see that here are the data sets that you have. Okay, these passengers have these attributes or features. So remember I said just now, for classification, spam and not spam emails, you need your examples, experience, task, performance, right? These are your experiences. This is your instance. This column, from time to time, I would sometimes call it a feature. Sometimes I will call it an attribute. Okay, so so here means that all of these are attributes. All of the columns are attributes. For the survived is a label. Okay, remember I said you need someone to label whether it's a spam email or not before you feed into the machine. You need to capture the machine breakdown time, whether the machine breakdown or not, before you train the data, right? So this is your label, whether this guy survive or not. So this is the supervised part that we need before we train our machine learning algorithm. Okay, so fear not, throughout the training I would write the code out by in my computer, so that I wouldn't go too fast, and you know won't be able to follow, right? As I write the code, you can see how I usually write the code, how and the thought process of writing that code, instead of just running the cells and just tell you what is it about, right? But yeah, but just now I was going through the first four cells quickly, because that is the the readings data thing, which would a lot of time you give a lot of lab errors. So I want that to be secure first before I really write the codes on my own. Okay, so let me go to the data understanding part. Some context to a problem. Okay, on April 15, 1912, right, Titanic sank after a collision with an iceberg. So kills 1502 out of 2224 passengers and crew, which is 32% survival rate. Okay, one of the reasons the shipwreck is due to not enough lifeboat for passengers and crew. Okay, so although there are some luck in surviving in the sinking, but there might be some obvious reason why this bunch of people have higher chance of survival than the other, which uh, is quite obvious sometimes, but we might want to capture the not obvious using machine learning algorithms. Then you can see that machine learning algorithms is not all about prediction. It can help you to understand your data more, can help you to give meanings to your data, and identify patterns that you wouldn't have observed before. Okay, you see what I mean by that. So for starters, right, easier way to uh, approach a machine learning problem is 7Cs. Okay, these 7Cs is not some well-known framework developed by the experts. Is is a suggestion from a book, right, called Data Science Solution. So maybe later I will show you the reference of where I get these 7C from, and you can refer to that. So if not mistaken, it's a book. So I want to give credit to that. But yeah, I wasn't referring to the book, I was referring to the Kaggle page, which we'll talk about towards the end of the workshop. Okay, but yeah, I just don't want to take credit of this. This one is some information from elsewhere. So Classifying is the first one, right? Is whether you survive the shipwreck or not, is whether your machine breakdown or not, is whether your data that you want to predict is a male or female, and etc. Right? The classifying here is not always classifying. Okay, it can be regression, which is what is the price of something something. It's clustering the groups of data points, right? And yeah, for the main idea of this first C, the classifying, is know what you want to do, the task that with the task, right? Remember the definition of machine learning: experience, task, and performance. This part focuses on the task, right? What is the result going to use for? What's the objective of doing this project? What is the goal we are trying to achieve? What is the direction that we are going to? It's very, very important to know what your objective is, and it shouldn't end just at the prediction part, right? For example, if let's say you have data coming in from upstream component, it, let's say your client gives you a district data, right? And you want to use this district data to predict the price of the houses in this district. Okay, then you do the job, you make your predictions, but do you know what the prices are going to use for? Does your client want to buy a house for themselves, or do they want to buy for a friend, or they want to buy for their kids, or they are investment company, they are REITs that they want to put the houses into their portfolio? These are different scenarios that, although the prediction is the same, but the uses after that is totally different. If they want to buy a house for themselves, you might want to be conservative in your prices, or it can be more luxury because they are rich. But if you are predicting the prices for a rich company, right, or a rich trust, then probably you want to come from an investment standpoint when you're doing your modeling, when you're making your decisions in your modeling process. Okay, so this is just to remind you that your goal shouldn't end at the prediction. Your goal should be the goal of your clients, of how they want to use it and what they are trying to achieve. Okay, correlating is the second C. So when we are making predictions, remember I said features is our column, right? This is one feature, this is one feature. Okay, so we want the feature to be highly correlated with our label. Label is this one, survive, right? Sex, age, all these are our features. Features supposed to have a high correlation with survive, right? If the younger you are, the higher chance you survive. That is an obvious information for us to make prediction of the survival rate. If the older you are, the higher chance of survival, that is some correlation there, right? But let's say ticket number is not going to have any correlation, because ticket is just a sequence of number of the ticket, right? So it's not going to be correlated with your survival rate unless your ticket tells something about you, which is the price of your ticket, the class of your ticket. That would mean correlation to your survival rate. But you might need some extraction from the feature, right? Not using it directly. And yeah, as the feature value change, does the solution state change as well? This is what I meant by the younger you are, the higher chance of survival. The older you are, the higher chance of survival. If you're in the middle, probably not, right? So this is the second point. The last point is multi-collinearity. It's a jargon for correlation between columns. So this is in contrast with the labels and the features, because the correlation between the label and features needs to be highly correlated, but the correlation between columns cannot be highly correlated. Okay, why? Because if, let's say, my fair price is highly correlated with survival rate, right? The more expensive your price of your ticket, maybe you are rich, maybe you'll be prioritized to go on the boat. If you are old enough, then because you are old, people will give you the chance to go on a lifeboat, right? But if the age and the fare are highly correlated, because you are rich, that effect will multiply on the survival rate, which will become unrealistic, okay? Or will add extra noises to your predictions. So in that case, this will cause a problem, right? And we have a name for this problem, which is multicollinearity. Okay. Converting is talking about data types. I talked about this earlier. Some algorithms can only read numerical features. Some can take both, right? So we want to manage the data type before we make our predictions, build our models. For example, this is a machine learning algorithm called logistic regression. Okay, for logistic regression, it would read numerical label from an axis, and then pass into a function called sigmoid function, which is the reciprocal of 1 plus exponential to the power of negative z, where z is theta transpose x. Forget about max here, because a lot of people is going to be frustrated when they see maths. So let's skip the maths for today, since we only have 2 hours, right? So yeah, this is how logistic regression, how this machine learning algorithm works under the hood. It passes your numbers into this function and convert into 0 and 1. And 0 and 1 is a probability of something. So let's say my threshold is 50%, and this is the age, or yeah, probably let's use the age, or maybe fare of a ticket. So if I pay two ringgit and a half, then I have a high chance of survival. If I pay -5, probably I do not have any chance in surviving, if that makes sense. So you get the idea. So this numerical, can only take numerical input. If you give data like male, female, how is this going to read the male and female? How am I going to calculate 1/1 plus e to the negative of male? Doesn't make sense, right? Unless I convert my male into 0 and 1, male, female. Then I can pass that 0 and 1 into that exponential function. Okay, that's what we are talking about when we say converting. So what I mentioned just now, right, converting male and female into 0 and 1 is called label encoding. Okay, the term is called label encoding. Imagine I have a column called country, and then I have 3 different countries, the India, United States, and Japan. So I would assign a number to each unique value. India will take the value of 0. US will take a value of 2. Japan will take a value of 1. So there's another way of encoding. It's called one hot encoding. It means we convert the value into 0 and 1. No more 2, 3, 4, 5, right? So instead, what we will do is, instead of uh, transforming into 0, 1, and 2 will transform into country India, country US, and country Japan. If it's India, the India will take the value of 1, the rest will be 0. If it's US, United States will take, United States will take 1 here, probably, and then the rest will be 0. If it's Japan, Japan will take value of 1, the rest will be 0. Get the idea? So, yeah, this is one hot encoding. Why do we need to have two different ways of encoding? Is sometimes the column is not good for label encoding. Label encoding is not good for that situation. Why? Because in some cases, like country, you are converting into ordinal data. What is ordinal data? Is a categorical, but there are rank between the values. 0 is smaller than 1 and is smaller than 2. 2 is greater than 1 is greater than 0. That is ordinal. But do I say that US is greater than Japan? Or Japan is greater than India? Or male is greater than female? Female is greater than male? That doesn't apply there. That's why in that cases, especially when you're using regression-based model, label encoding is not advisable because of these ordinal issues, right? So we'll change into one hot encoding, which do not have any ranking. You just show 0 and 1, whether it's this number or it's not this number. Okay, then you do not have a comparison of values. But sometimes there are challenges to one hot encoding as well, which is the dummy variable trap. Okay, remember just now I said that the features shouldn't be correlated, right? Otherwise, you have a multi-collinearity problem. But if it's India, the country is India, then it's impossible to be United States or Japan. If it's Japan, it's impossible going to be India and United States. In this way, it created high correlation between these three columns, right? Because if not India, then United States or Japan. If not US, United States, then India or Japan. That is a very, very high correlation. So in this case, what we can do is to reduce this problem, we would remove one columns. So 1, 0 means it's India, 0, 1 means it's United States, 0, 0 means it's Japan. Okay, that would help solve the multicollinearity problem. Then at the end of the day, whether we should use label encoding or one-hot encoding, we apply label encoding when the categorical feature is ordinal, like low, medium, high temperature, okay, that or the age lesser than 50 years old or higher than 50 years old, that can be ordinal. Okay, that in that case, we will use label encoding. When do we use one hot encoding? When it's not ordinal, okay, and the category feature is less. Because if you have a lot of columns, one hot encoding is going to create even more columns. Remember I said that when your number of columns increases, your model gets more complex, you requires a lot of computing power, and it's very costly to do that. Okay, so that's another thing you want to take note as well. And most of the time, categorical to numerical data type conversion is due to algorithm needs. Okay, a lot of models cannot read categorical data, and a lot of time, numerical change converting to categorical is seldom. Okay, but it does happen because we want to reduce noise or improve performance. Okay, so this is an example of converting numerical data into ordinal data. Okay. For example, I can change age. If age is lesser than 16, I'll change to 0. Okay, I'll label as 0 age. If it's greater than 16 but less than 32, it'll be 1, and then 2, 3, and etc. Okay, so this would help me to convert my age into categorical data instead of numerical. Okay, the last few C's is completing, replace the missing values. To replace the missing values, we have a few ways to do it. Either we delete the rows or we delete the columns. Okay, but a very common way of doing replacing a missing value is central value imputation. So for central value imputation, what we are going to do is we'll replace it mean, mode, and median. Okay, mean, mode, and median, so that it would represent the whole group with the central value of the sample data. Okay, conditional imputation is also replacing with central value, right? The idea of central value imputation is we make a guess, right, that would most of the time be true if we are guessing the missing values blindly, right? Imagine if I'm a teacher and I ask you, hey, what how is your class doing? How are your students doing? Am I going to read the result of my students one by one? Oh, John gets 63 percent. CT gets 50% score in the exams and blah blah blah. But that's not going to be the case, right? Most of the time, I will just say, oh, most of them they get 80 marks and above. That's central value, right? On average, I earn 1 million a day on average, right? That is central value. Because when we want to give a number to represent something, we want to make our best guess, right? That's why central value is always a good choice to go. But sometimes it's not that good as well. In this case, if I have a luxury class vehicle and a low budget class, so let's say I have these missing values in a luxury class. Am I supposed to get the average of the whole column or just the luxury class? Should I include the low budget into my averages, or should it be the average of the luxury class only? Okay, so in this case, this is conditional imputation. Okay, when I predict a luxury class, replace the missing value in a luxury class, it doesn't make sense for me to include the low budget into my average. So I'll calculate the average of the luxury class only. Okay, so this is conditional imputations. Normal imputation and conditional imputation. That's the difference. And another thing we can do is we add a flag to our imputation. Okay, it means after I replace the missing values, I add another column to tell the machine that it was missing before. Because if you look at this, the bad, two bad and two bad here might look the same without this column, right? Then these two columns, these two rows might be treated the same, and sometimes it might not be the right thing to do. So we will add another column indicating that it was missing before. Then these two rows are treated differently because of this flag. Okay. And predicting the missing values. Since we are replacing missing values with some numbers, most of the time we are guessing the numbers. So if we are guessing the numbers, why not we let the machine to guess the number for us? This is predicting missing values. We use other features that are not missing, build a model, and the task of the model is to purely predicting the missing values, is to replace the missing values for us. Okay, correcting can fix obvious errors, fix the outliers, removing them, and errors might add noises to your data. So if your task is not anomaly detection, it's not finding abnormal data, then probably you might want to remove them. And creating new features, we would talk about, I'll show you this later in the practical part. So how do we do it? For creating columns. For example, I can create a column, say that it shows true if age more than 60 or age less than 19, right? This is called binning, converting age, which is supposed to be a numerical column, into categorical, right? And I can probably create a column called family size to add the parents, children, siblings, spouse, and themselves together. And I can compare the survival rate to see if that is significant or not, right? So this is creating, and the last one would be charting. For charting is visualizing your data with plots and charts, right? So charts or data visualizations is very, very important before you do any analysis, before you do any modeling or any prediction. Okay, because if you don't understand your data, you have no way to analyze your data without visualization. Okay, so all this I will show you all of this in the practical later. So let's understand the data first before we get our hands dirty in the data, in the practical, okay, and the codes. So the data here, if I've run my data, all of these are the column names, okay? And this is a data dictionary to describe the data for you. Passenger ID is a unique ID of each passenger, self-explanatory. Survived is whether you survived or not. P class, okay? P class is ordinal because the number tells you the rank of that class, of that person, right? So yes, the number can be ranked. Then it is an ordinal data. Name, sex, age, self-explanatory. Okay, SIP-XP. SIP means siblings, SP means spouse. Okay, the numbers of siblings and spouse. Part, parents and children. Okay, ticket is a sequence of ticket number. Fare is the price of the ticket. Cabin is which room the passenger stays in the Titanic. Embark is where they go on board of the Titanic. Okay, 3 port. Okay, embark is a port of embarkation. So with that said, let's go to our practical without any delay. Okay, so how would we do this is, I would create a new notebook. And from I would try to write most of the code from scratch so that you will see the thought process of writing it. Okay, but the answers of all of this is this one. Okay, the Bible for this workshop is this. This is the Bible of today. For today, anything that is contradict to each other, refer to this. Okay. Okay. So first thing we are going to do when we are starting our prediction or projects, right, is to get the data. So here I upload my data. Into this place. Okay, create a new folder called data. Move this in. Okay, we try to be consistent with the Bible here. Okay, the first thing we are going to do is okay, let me create a new text down below. This one I would delete this. Okay. First thing, if you're using a notebook-based IDE like Jupyter Notebook or Colab, document your code well, like what I did here. Okay, so first I would import all my libraries. Okay, import all my libraries. What I'm going to do, I'm going to Control A and Control C, Control V, run it here. Okay, because there are a lot of libraries that we're going to use, so let's just not waste time on typing them out. Okay. Next, we want to acquire our data. So add a text here, hashtag, type acquire data. Enter to run. Okay, and then we would do this. When we acquire our data, we will need a library called pandas. That's why we import pandas as PD, so that we can define our train data frame equals to PD dot bit underscore CSV. Okay, bit underscore CSV is a function in the pandas data frame. So we can use this to read our CSV and pass the file directory. We are going to read the data folder here, / the name of the folder. It's called Titanic Train. Okay, so we're going to type Titanic underscore train. Remember the file type .csv. Okay, then usually I would copy and paste for my testing sets. Test underscore pf. Okay, then I would name this to test. Okay, usually this would be all, right, for a newbie. But with experience, we might want to add this thing to our code. So we would combine them in a list. Okay, in a list for train df is the first element, test df is the second element. Why do we need to do this? Because we are going to do a lot of data transformation, data cleaning, and so on. So we don't want to repeat that data preparation 2 times for training and testing data. right? So if we put them in a list, we can root through the data and apply the same data preparation to that. So now I've read that thing, I want to know the number of rows and columns. Okay, so to know the number of rows and columns, we would use dot shape, train df dot shape. Okay, we have 891 rows and 12 columns. If you look at my notebook here, it's very comprehensive. It's very organized that I even write the description of everything out, but I don't usually do that. I do that for the sake of this workshop for you to know what I'm doing, right? But yeah, this is reality and this is expectation. So this is what I usually do, but for you, you can copy and paste this into this, so you really know what's going on. This one, I just want to check the data type of this if it's a list or not. Okay, it's good to go if it's a list. Now we can preview the data. When we want to preview the data, we call the data frame, right? You can either type the name out, Control Enter. It will show you everything. Of course, not everything because it will summarize in dot dot dot. But yeah, usually what we would do is we will put a dot head at the back. Okay, dot head by default it will show you 5 rows. Okay, it will show you 5 rows. Then you can roughly look into what is happening in your data. Okay, so this is a very useful function. Now we are moving on to data understanding. Okay, add a code. Sorry, you should add a text. Document your work, right? Data understanding. Usually in Jupyter Notebook, you can use Control Enter. So that's why I was confusing. Okay, next. First question, we want to answer which features are available in the data set. Okay, just put a comment. Which features are available? So when we want to know the columns, okay, we would use dot column dot values. Dot columns with an S dot values. Enter. NumPy array is not callable. Sorry. Yeah, parentheses. Okay. And because it shows you in an array, it doesn't look very good here. That's the reason why I add a print in front. Okay, you see that? That's the reason why we need a print. But usually, if you don't mind that array in front, you wouldn't need that print. Okay. Checking for converting and completing. That's the first step we are going to do. Okay. And a very useful function for this. Oh, the reason why we need the column names, right? You might be curious why, because I already have the column names here. Why do I still need this? Sometimes it's even good for us to store this into, let's say, calls. Okay. Why? Because sometimes we want to look through the column names or something, right? You will know why later. You are going to need this name all the time. So it's better to even store in a calls. So when you forgot the name, you need to call it out. You can call the calls again. Okay. Then checking for the data type, checking for missing values. Very useful functions is called train_df. The method is called info. Okay, using info, you can check the null value. Our unique ID is passenger ID, and passenger ID has 891 rows. Out of these 891 rows, age only have 714 non-null. It means 891 minus 714 null values. Even worse for cabin. Okay, a little bit for embark. That's why here I said that 177 missing values, 687 tremendous numbers of missing values, only 2 missing values for embark. So let's make the obvious easy decision first. The easy one is cabin. 887 out of 891. We can straight away exclude the column. Okay, no need to look at it. For embark, because it's only 2, doesn't matter what we do to them. It doesn't affect anything. So we just replace with our central value, which is the mode of the variable. Age is a tricky one. Oops. Age is a tricky one because if we replace missing values with a random number or something, it would add bias to our model. Because that number, that 177 numbers, we don't know, but we give a number to that. So that way will create a bias. So, but we cannot do the same like what we did to cabin, because age, like I said just now, might be useful, right? Infants, babies, or old folks might be given priority on the lifeboats. We don't know yet for sure for now. So we are going to figure this out later. Okay, so easy decision, drop the cabin column, replace the embark. Hard, difficult decision, age, we will look at it later. Then what are we going to do next? Come here, Control A, Control C, add a code. I need to check the unique values. Okay, I need to check the unique values. So train_df dot unique. With an S maybe. Oops. Train_df dot n unique. I see. And oops. Unique. So you see, this tally with our guess just now that passenger ID is the unique values. Now I see that name is unique as well. You don't have anyone with the same name. Survive, P class, all of them, they have their own unique values. Okay, tickets, 681 unique values is almost 891, right? So we can exclude ticket because it doesn't give any information to our survival rate, because almost everyone has their own different ticket number. Okay, that's the information we can get from the train DF. So for the sake of learning, you can do this to check both training and testing sets. Okay, but usually when I was doing my project, I won't do this. Okay, even if I do, I'll just copy and paste from somewhere. Okay, but usually what I do is just this in reality. Okay, so we are going to drop cabin and ticket as we said just now. So how are we going to drop? Before we need to drop our ticket, we want to check the shape first. Okay, combine 0 shape. Remember, combine 0 is our train DF, right? So I think I will better copy and paste instead of typing them out. But what I would say here is when I want to drop something, I would I would do it like this: train underscore df dot drop. Okay, this is the method we use. What's inside the drop is what you want to drop. Okay, so if let's say I want to drop a column, I would just use a square bracket, type the name. Okay, now I have 2, I'll just add another one. This is what you do when you want to drop something. When I run, oops, not found in your axis. Oops, yeah, by default, axis equals to 0. So when I say axis equals to 1, it's the column. Right? By default, the drop is for rows. Now, when I change to axis equals to 1, it becomes the columns. Now you see that my train DF do not have ticket and cabin anymore. But is that true? If I type in the next row, train DF, oops, you see that ticket and cabin is still here. Okay, that's the reason why we need comma in place equals to true. I wouldn't run this. So I wouldn't run this. Just now I run this because I know it won't replace my train DF. But now that I know it's going to replace my train DF, I wouldn't run this first because I want to copy and paste this into my thing, right? I was explaining this thing to you. Why do we need axis equals to 1? Why do we need in place equals to true? Okay. What about the for loop? Remember, we want to apply this not just to our training set, we want to apply to our testing set as well. So for each element in combine, I will run 2 times, right? First time is for training set, second time is for testing set. Okay, then for each training set, I will drop ticket and cabin in place equals to true. Then I'll compare the shape before and after. Okay, 12 column initially become 10. 11 column initially become 9. Okay. Now that I've explained this to you, I'll just copy and paste this, and now I can run. When I run train DF again, this time we do not have ticket and cabin anymore. Okay, that's why we need in place equals to true. Do let me know if you cannot follow, if questions. The videos you can rewatch after this in our YouTube channel, Quantetics Academy, anytime, right? It will always be there. So feel free to watch it again for practice or for your revision. So next, what we are going to do, we are going to drop passenger ID and name. Because they are unique identifier, so it's not going to do anything good to our to predict our survival rate. Your name is not going to tell whether you are surviving or not. Your ID is not going to tell you are surviving or not. So that's just copy and paste. It's identical to the previous one, except that for the column name. So we just run without any explanation. Now we have 2 columns lesser. And finally, we can check the columns that we are left. Okay, so you can see that train and test DF, the difference between them is the survived, right? Because you're testing data shouldn't have the answer. When you're doing your test, you shouldn't have an answer to your test, right? So that's why. Then we would start replacing missing values. Okay, so I would add a text here to say that this is replace missing values. To replace missing values, remember we already dropped typing. So now we only need need to replace embark. Remember two missing values. So that's the easy one. Let's do that first. What we are going to do is we need to replace with the mode of that column. So we need to calculate that value first. Train underscore df. Okay. Not embark. The column name is called embark, right? Dot na dot mode. Okay, because we want to calculate the mode, so usually we will need dot mode. But when we are calculating the mode, we do not want the missing values to affect our numbers, right? So usually we would drop the null value first before we calculate the mode. Okay. Now we run. Okay, can you see this? It have 0 and 5. Okay, 0 and S. S is the it's not 5, it's actually S, right? So S is our port name. So if we are going to take 0, we're going to get S only. Okay, we're going to get S only, which is the answer to our question. What is the mode? Okay. Here we will assign this to an object called frequent port. Okay, save this to an object FREQ. And then we are going to replace the missing values for both training and testing set because both of them should have missing values. So I will loop both my data sets again. Okay. Usually when I want to replace the missing values, I would use fill NA method. Okay. For example, train underscore df dot fill NA. But when you are filling the NA, which column do you want to fill? So it will be embark. Okay, train df embark dot fill NA, but what do you want to fill with? We want to fill with the frag port, which is the values we calculated just now. Okay, this is what we would usually do to replace missing values. But now that we have two data sets, we need a loop. So it will become like this instead. Okay, we run it. Now is the part here whether we want to drop the age or not. Quick answer, no, we shouldn't drop, but I'll give you the justification later. Okay, so we will skip the imputing age first. We'll skip it first because we are going to, I want to give you a justification first. Okay, so let's print this. Let's print it to check our missing values. Okay, no missing values for all columns except for age. Same thing here. Oops, I have another missing values for fair. Okay, so in this case, it's just one missing values, right? So what I'm going to do is I'm going to remove that. Okay, I'm going to remove that from my column. So I'm going to use dot drop NA. But since I only have one, right? So later I'm going to drop this column once and for all, but not now first. Okay, not now. Just be aware that we have these missing values here. Then we can go on. Okay, we'll come back to deal with the missing values. So for charting pair plot, we are going to need to import Seaborn. Okay, and this pair plot, oops, this is a code to run a pair plot. Let's give it a second to run. But we are expecting this result. Okay, the pair plot is going to give us to look at this in a glance. What is the distribution of the features corresponding to each other? Okay, corresponding to each other. You can see the scatter plot, you can see the distribution, Gaussian curve here in the diagonal, because in the diagonal is the data distribution according to itself, right? The hue here is colored the data points by your label. We want our survive or not survive in different color so that we can see what we can see here. The blue color spikes here in P class. What remember? Do you remember what is this? P class is 1, 2, 3. 1 is upper class, 3 is the lowest class. And without fail, the upper class has higher survival rate. Lower class, we have tremendous of non-surviving rate, right? Which is not surviving, unfortunately. So these are the information we can get here. What else? Age. As expected, if you are a baby, most likely you can survive in adolescence. If you are adult, most likely you will not survive. This one can already tell us, or just this can be a good justification enough for us to keep the age column instead of dropping it like we did to cabin, right? And this part is parents and child, right? If you have, this is supposed to be 0. If you do not have any parents and child, you most likely you will not survive. But if you do, most likely you can have a higher surviving rate. Okay, so on and so on and so on, right? This we can delve into this data distribution one by one, and it's going to take a very long time to fully interpret this thing. So that's why I have written everything you need to know. Okay, inside our Bible, here, all the results here. Okay, that are noteworthy. So for the sake of this workshop, we will continue to read the data distribution. Okay, first we are going to get the surviving rate. Okay, this one I won't go through on how to build the chart, because if you need, you can just copy and paste mine. Okay, and you can replace this with whatever you want to train. Okay, this one is just a title. Whatever you want to change, you just change here. Okay. When I run this, it's a horizontal bar. Why is it a horizontal bar? Because I put a y equals 2. So the